The rise of the machines is just around the corner. Robot technology is moving into a whole new world. It is the stuff of science fiction. But should we fear the robot of the future? Or welcome innovation designed to make life easier for us all? In the near future, robots may run our world. They could manage our cities, our money, even the details of our private lives. They don't have minds of their own, but could they? If they did, what would happen to us? We've seen it at the cinema. Man wiped out by creatures of his creation.
For example, in the movie 2001, we had this beautiful spaceship with the state-of-the-art computer technology, and HAL was to carry out all commands given by humans. However, you know how humans are. We're messy. We give sloppy commands, and commands were given to the computer that logically could not be carried out. And so the robot said, well, if the humans give me orders which cannot be carried out, the only logical way to carry out these ridiculous commands is to eliminate the humans. And that's precisely what the robot did.
That's the problem with robots. No common sense. Man's innate ability to think, decide, and act has not always served the human race well. But wouldn't a world run by robots be worse? Much worse.
If there's an earthquake, all of a sudden we have a shutting down of the water supplies. And the robot will say, well, we must take care of all the fires that are breaking out. It'll divert all the water to taking care of the fires. And at that point, there's going to be a massive dislocation in the water supply inside a city. And the robot will simply not know which catastrophe is more important than another catastrophe.
But such scare stories aren't slowing down robot research. In Japan, scientists are competing to recreate the human race in metal, plastic, and silicon. This is Asimo, the first humanoid to walk out of the laboratory and into the real world. It's designed to look friendly, not the kind of robot who'd zap us with a laser. Every step Asimo takes has to be pre-planned, and its batteries only last for an hour. But it's taken nearly 20 years to get this machine up and walking. Masato Hirose was the project's chief engineer.
It's our dream to come up with a robot that could be useful in people's everyday lives. I am 46 now, and it would be nice if I could make Asimo into the kind of robot I could use myself in the next 10 years, by the time I'm 55.
Asimo's predecessor started off as just a pair of legs. Even so, he was a top-secret project. Scientists didn't want anybody to see their progress or witness their failures. This robot, built in 1986, could only walk in a straight line and needed nearly 20 seconds to take a single step. Picking up the pace was a huge challenge. To walk upright, a person uses 200 muscles, all controlled by the human brain. For a top-heavy robot to walk on two legs, its computer has to perform a constant balancing act.
No matter how many times we tried to do this, it always fell over. We refined it day by day, over and over again, and finally got the robot to walk.
Engineers spent years monitoring human body movements and then programming their robots to recreate them. It took 4 years to get the speed up to 1 kilometer an hour. It took another 2 years to get the robot to cope with slopes and stairs. Finally, in 1993, there'd been enough progress to attach the legs to something that looked like a body. P1 was almost 2 meters tall and weighed 180 kilos, twice the average weight for a man that size. But its successor, P2, was much lighter and more compact.
The first time I saw Honda P2, I was impressed and amazed. It was walking without wires, Everything was self-contained, onboard computers, onboard batteries. So it was impressive on that level, but also just because Honda was able to keep it a secret for 10 years.
This is the latest model to emerge from the lab, and is a sign of what may one day be in our homes. The quest to build the first artificial human is highly competitive. H7 is the result of a multi-million-dollar research project funded by the Japanese government. The objective? The creation of humanoid robots capable of performing complicated tasks, like playing football. Keeping your eye on the ball and kicking it with your feet may be child's play for humans, but it's a major advance for machines. James Kuffner developed much of H7's software.
If I tell my daughter to go fetch my keys from the kitchen table, I don't have to tell her, move your left foot in front of the right foot, turn 90 degrees, and then enter the kitchen door. She can do that automatically, and we'd like to get robots to have that level of autonomy.
H7 can track the ball with its eyes and make its own decisions about how to follow, catch, or kick it. But there are limits to what it can do of its own accord. H7 may have mastered football, but it's not so good at other sports. A whole new set of software is needed just to get H7 to pick up a bat. H7 doesn't find the bat by using its camera eyes. Instead, every movement is planned in advance and written into its software. H7 is no use if the bat is put in a different place. The most intelligent robot in the world still can't match the coordination and agility of a toddler.
The software that I wrote for H7 took over 5 years to develop and over 100,000 lines of code. And that involved getting the robot to move, pick up an object and put it from location A to location B. It didn't include object recognition, speech recognition, other kinds of sensing like computer vision functions. Robotics research has a history of constantly reinventing the wheel. Every time a new machine was developed, they had to write again from scratch the software to control it. So I really believe that we're not going to be able to make progress in robotics without some way to build upon the lessons learned.
Despite the challenges, scientists are pushing forward the development of humanoids, believing there will soon be a need for them in the home and the workplace.
If you take a look at the Japanese population, it is aging rapidly. Labor is extremely expensive. In the United States, because we have a large immigrant population, cheap labor is not such a big problem. Why be satisfied with a mechanical maid or butler when you can get a real maid or a real butler?
But in Japan, mechanical servants have a bright future, and not just in the home. Which is why the Japanese government is funding the development of industrial robots. HRP-1 is a remote-controlled robot. In the future, versions of this robot could replace human workers on construction sites. HRP-2 is designed to help people with heavy manual work. It's remotely controlled by instructions given through a headset. Creating a robotic workforce could be big business, a real boost to Japan's economy. But there are still a few snags to overcome. Staying upright is a delicate balancing act. Humans who have 10 billion neurons in their brain have spent over 2 million years learning how to do it. Morph 2 is a miniature humanoid, not always on its toes. Like a human, it can sense when it's off balance, but it's not always successful at compensating. But when it does manage to stay upright, its range of movement is impressive. A whole new meaning to agility tests. This is Morph 3. Its incredible flexibility is made possible by 26 joints, all coordinated by 133 sensors and gyroscopes, which detect changes in pressure and position. But they can't process all that information as quickly as humans, which is one reason they fall over so often. While humanoids are still being developed, other robots are already being put to work. PackBot is a robot designed to help the police or armed forces in dangerous operations.
One of the classic situations for the PackBot is a situation where a bad guy has barricaded himself inside a building and a police force is outside looking to make an entry. And they have very little information about what is going on in that building. So the robot is designed to climb stairs, climb into that building, look around, essentially put eyes and ears inside that building, give an idea where the doors are, where the stairway is, where the bad guys are, how many bad guys there are, if there are good guys, and if the bad guys are still alive.
PackBot can be controlled from almost a kilometer away. It's a versatile robot, equipped with cameras, microphones, infrared sensors and sonar. The satellite navigation system tells its operator where it is, as well as the roll and pitch of the terrain.
We're looking at adding chemical sensors, bomb detection sniffers, mine detection platforms. Basically any kind of sensor that you can come up with, we can incorporate on the back of the robot.
PackBot is housed in an impact-resistant aluminium shell that can survive a 3-meter drop onto concrete at extreme temperatures. It can move at speeds of almost 20 kilometers an hour and through 3 meters of water. If it lands upside down, its flippers turn it over. One reason it's so tough, it has no wires that might break or become disconnected.
I'm at the landing, clear at this point.
Stairway clear?
Clear.
1, 2, 3. Go.
This is only a police exercise, but PackBot has already seen real-life action, having worked at New York's Ground Zero, helping in the search for survivors.
And this is particularly important now where the loss of human life isn't tolerated anymore during war or military action, or civil action for that matter.
Scientists are already working on the next generation of PackBots, with even more capabilities. The development of an extending neck will enable the robot to peer around corners.
I'm turning the robot.
Okay, Tommy, what do you got?
2 people, 1 suspect and 1 hostage. He's got a knife in his right hand. There's a female on the ground.
Go.
At the moment, PackBot works alone. But there are situations when it will be an advantage to have a whole team. This is becoming possible with new technology called Swarm. This group of little robots works cooperatively. At the moment, they are playing Follow My Leader. The inspiration for their software, the behavior of ants and bees.
In nature, 20 million individuals in some of the larger societies of ants all come together and work for a common goal. And they don't have cell phones, they don't have internet, they don't have GPS, but yet they're able to work together collectively and to do complex things like map their environment, form paths, carry food around, communicate information to their nest mates, things like that. So we're trying to get some of that intelligence into robots.
Swarm bots can talk to each other without human control. Follow My Leader makes communication easy, especially underground where radio links don't work. The swarm can pass messages through each other until they reach the surface.
One robot can say, I need 5 robots to follow me, and 5 robots will run and compete to be the 5 that get to follow, and they'll follow this robot like a train. If one of the robots fails, maybe its motor dies, or maybe it gets caught in a crevice, the world is very difficult. It doesn't matter, because another robot can just jump in and take its place.
Teamwork means the swarm can spread out at speed, covering a wide area quickly. The robots can create an up-to-the-minute moving map of the disaster area.
So, for example, you could put a lot of swarm members into a burning building, and they could spread out. And they could all have sensors that say where the hot spots are, where the smoke density is, where people might be found. So you've got this map that's growing very quickly. One robot wandering around could never do that.
Ultimately, the goal is to construct thousands of swarm robots, clever enough to take on intricate tasks in difficult environments, such as searching for landmines, rummaging through rubble in the aftermath of an earthquake, or even exploring forbidden planets, like Mars.
Another idea is that by having a large number of robots, they can all be relatively cheap. It's not so important if one of them breaks. So now, if you wanted to have a mission on Mars, for example, imagine dropping 1,000 robots. It doesn't matter if 80% of them fail when they're dropped. There's still 20% down there that are running around collecting information. Whereas if you just had one very expensive robot and it broke, the mission has failed.
And with these uncomplaining automatons doing the dirty work, there's no risk to human life.
Robots can withstand the stresses, the strain, the radiation, the deprivation that exists in outer space. They don't complain, they don't require life support, and they don't have to come back.
But space research will have job opportunities for bigger robots too. Robonaut is a remote control robot developed by NASA to work outside a space station where there's danger from space debris and cosmic rays. Safe inside the space station, the astronaut wears a special visor and glove. When he turns his head, the robot's head turns too, and sends back video images of what it can see. When the astronaut moves his hand, the robot mimics the action. One advantage of humanoid robots is that they can work with tools and equipment designed for people to use. But if you don't live in a space station, you might want something a little bit friendlier around the house. How about a robot that could greet you at the door? This is Papero, the first domestic robot, coming soon to a high street near you.
Hello. 調子はどう? I'm fine, thank you. Yahoo!
Papero stands for Partner Personal Robot. It's a PC on wheels. It could act as your personal secretary. It can take voice messages, send and receive email, even operate the TV.
6チャンネル. Hi, hi.
Papero is programmed to respond to human requests. It recognizes 650 voice commands and speaks 3,000 phrases. It recognizes people by their faces and recalls facts about them, like their blood types and birth dates. You know when Papero is listening to you because its ears turn green.
Papero can easily be linked to the internet or telephone. This means that humans can check what's happening at home when they're away. For example, if you can't remember whether you turned off the gas cooker, you can use Papero to see pictures inside your house. You can also check on your pets at home.
And because Papero is compact and on wheels, it's very stable. It won't crush small children or trip over pets. And if it does bump into something, it's unlikely to do any damage. Papero likes to be stroked. This tells it that you're pleased, and it remembers its good behavior for future occasions. And if you need a dancing partner, Papero is definitely for you. Papero can be as endearing or as irritating as a 2-year-old child. But it has one great advantage over any toddler. "20 years of research have gone into today's robots. But are they ready to join the workforce?
Our robots today have the collective intelligence and wisdom of a cockroach, a retarded cockroach, a lobotomized retarded cockroach. However, because of the doubling time of computers, I think that by the year 2020, we may have robots that are as intelligent as mice, perhaps as intelligent as a dog.
If robots are really going to be useful, they're going to have to learn how to learn. The dream of developing a human robot has endured for decades, and substantial progress has been made. Now they can talk, walk, and sometimes outsmart us. Playing chess against a grandmaster demands intellectual skill. But in 1997, the world's greatest chess player, Garry Kasparov, was beaten by a computer called Deep Blue. So, if they are so clever, why haven't we put them to work yet?
The real problem, why we don't have mechanical maids and butlers, is the common sense problem. Things we take for granted are almost impossible to perform by robots. We know that water is wet. We know that strings can pull, strings cannot push. We know that when you die, you don't come back the next day.
It would take experts centuries to program a robot to have the common sense of a 2-year-old. So now, robot designers in America are trying a different approach, getting them to learn. Cog is a robot that, like a baby, is learning through experience. Cog has several cameras. Through them it can see objects in wide angle or close up. It can track objects, sense and depict color.
You see, robots can see. In fact, robots can see about 10 times better than you can see. But robots don't understand what they are seeing. They don't understand anything more than lines and simple geometric patterns.
At first, Cog didn't know where its arms stopped and where an external object began. But by seeing and poking these toys, Cog is slowly learning the map of its own arm and how to distinguish a particular object from the background. Cog now knows that cars move forwards or backwards, not sideways. So, even when the car is placed in a different direction, Cog hits it from the front or back. If robots can learn from experience, they won't have to be programmed for every task. But this initiative is still labor-intensive.
We'd like to be able to take that robot in the future and show it, here's how to do the ironing. You know, you fold it this way, you do that, and that's how to iron. You do it now. We'd like the robot to understand that, be able to map it to its own body and do the task.
This is K1. K1 isn't doing the ironing yet, but it does try to copy its programmer's workout. Judging by this performance, no one is going to let it loose on the ironing for some time. Copying is just the first stage of developing intelligence. If K1 is ever going to learn how to do the ironing, it will not only have to know how to hold the clothes and move the iron, it will also have to understand that the aim of the exercise is to get the clothes free from creases. To achieve this, K1's designer, Yasuo Kuniyoshi, sees a future where robots will grow up and learn alongside humans.
This might sound like a science fiction story, but I'm talking about a very long term ahead, the far future. It can happen that newborn human babies are assigned partner robots from the beginning and then grow up together with a robot.
A robot would learn its human partner's likes and dislikes and adapt its behavior accordingly. But that's a long way off for K1. After all that exercise, it's time to strip off and cool down.
Here. Okay, you go, dude. Now you're playing.
Darren Bentivegna is teaching DB to play air hockey. DB's camera eyes have been set up to track the puck's bright colour. So far, so good. As long as the lighting conditions don't change.
Now you know how to play it. All right, getting a little better.
But to play the game, DB not only needs to see the puck, but to predict where it will be a few seconds later.
That's my score. The puck not always can be seen. Sometimes it goes underneath an arm or it's in a corner. So when this happens, DB cannot see the puck anymore. So it's almost as if you were to play air hockey and somebody was always to do this to you. So you're trying to predict, and then all of a sudden somebody covers your eyes, and then they take your hands away, and now the environment has changed. Yeah, okay, now hug the puck now. Give it up.
Once DB has learned how to keep an eye on the puck, it then needs reasoning skills to decide its strategy. Having chosen its shot, DB needs the motor skills to execute it. And all these seeing, reasoning and action skills need to happen instantly. The puck waits for no man and no thing. Is it worth all this effort just to teach a robot a game?
Through verbal communication, you could tell DB or teach DB new skills, as you would teach a person. So, for example, if you wanted to have DB do ironing in your home, you would have DB in the location, and you would tell DB, watch DB, this is how we iron. We take the iron, we move it across the clothes, and we look for the wrinkles, and we make sure we don't burn. And it would know about all these items through these communications, and little by little build up more and more skills. One day you'll be able to play as good as this. Well, I'm hoping you'll be able to play better. But it's very important that, of course, that you teach your robot well and that it learns well, because you can have things as your robot trying to cook your dog or burn your clothes or break your dishes, and of course this is not what we want.
If robots could learn and repeat tasks just by watching, they could become invaluable in the workplace. Other developers are taking the concept of a human robot one step further. They hope to produce a robot that not only copies our movements, but also our emotions and facial expressions. Fumio Hara directs the Faced Robot program at Tokyo's Science University.
The easiest expression to replicate is excitement. The corners of the mouth move up and the eyes go down slightly. But for surprise, the eyes get bigger and the mouth opens, like this. And for fear, you're scared. Everything tightens up, and the eyes are slightly bigger, and the mouth horizontal.
Not exactly a pretty face, but a functioning face, the first of its kind in the world. Silicon is stretched over the skull, made up of semiconductors, wires and pistons. The wires have to be positioned in exactly the right place to replicate the muscles in a human face. But expressions like fear, surprise and anger use similar muscles and can be difficult to tell apart. So it's hard to make the silicon look expressive.
We call it virtual communication. We just want to find out how well a machine can fool people by creating realistic expressions.
Hara believes that a great deal of communication is through facial expression alone. To communicate effectively with humans, robots will need to express feelings we can understand. With the help of tiny video cameras mounted behind the eyeballs, this robot can already read human faces and copy what it sees. It's programmed to recognize and recreate 6 emotions. But Hara wants to give the face a voice so the robot can not only look angry, but sound angry. Meet WE4, Mr. Personality. It really seems to enjoy tracking a red ball and doesn't like being ignored. It shows surprise when the scientist opens a bottle of vodka, but it does like the smell. WE4 can make expressions of disgust, fear, anger, surprise, sadness, and happiness. Once a robot can express these reactions spontaneously, it will be well on the way to having a personality.
For successful communication, the key issue is compatibility. 2 incompatible people are not likely to become lovers or marry each other. The next step is to make each individual robot's personality harmonize with individual people.
Rodney Brooks is developing a sociable humanoid robot he calls Kismet.
Do you want to talk to me today? What do you think?
More than that.
I'm too close? What if I get this close to you? What do you think? Right now, Kismet is modeling a very young infant who doesn't really have language. So it babbles and does turn-taking, as you can do with a young infant, back and forth. But there's not too many words that it understands, and it can mimic a little bit, and we're having it learn about simple objects by talking to it. Can you see me?
Yes.
No, that's a bright light, isn't it? You're much more interested in the bright lights than my face today. Come over here.
Kismet engages with people through an expressive face-to-face interaction. Brooks was inspired by infant social development and psychology.
Hero.
Kismet has a bunch of different emotions, and it will react differently to the same stimulus depending on what emotional state it's in.
Sad.
So we never know from minute to minute or even day to day how it's going to interact with us.
Then, well.
Hello.
Hello.
Do you like me?
Yes.
Kismet was designed to react to social cues and learn from a human instructor.
Kismet, say horsey. Say horsey.
Horsey.
Good robot. There you go. Yes.
Yes.
Yes, Kismet.
15 computers are involved in making Kismet either bored, lonely, stimulated, tired, talkative, or silent. It's still only a rudimentary personality, but robots are slowly becoming more and more like humans.
Very smart robot, Kismet.
I think we'll still want plenty of robots that don't have any emotions. My refrigerator works 24 hours a day, 7 days a week, and I don't want to feel sorry for it having to work so hard. But I think there may be some roles for emotions in robots that we want to interact with on an everyday basis, because it's a very intuitive way of us understanding what's going on.
Robots are already in the workplace, and they may soon be in our homes. But what about more intimate, life-changing involvement? Eric Harper looks like anybody else. But one part of his body is completely robotic. 9 years ago, Eric lost his right arm in a printing press accident.
The day I lost my arm, I had been working late. The rest of the shift had gone home, and I jumped up onto the machine and actually fell in and was drawn into the machine, and then it shut down. My arm's stuck in the press, and day shift isn't going to come in till 5:30. So I have 4 hours to wait.
Eric was eventually rescued, but most of his right arm had to be amputated.
I was right-handed, and having lost my arm, it was like, oh, well, this is going to kill me? No. I'm going to go on. I'm going to do what I want to do. I have a life to live, and it's not going to stop me.
The robotics in Eric's new arm are designed to respond naturally to his body movements. The arm consists of microprocessors, circuit boards, motors and gears. It weighs nearly 3 kilos. Electrodes in the socket receive electrical impulses from what's left of Eric's muscles. A valve seals the vacuum inside his false arm, helping to keep it in place. A computer reads the electrical impulses from Eric's back muscles and bends his robotic elbow, raising his forearm. Eric can make his hand close by flexing his biceps and open by flexing his triceps.
Like all robots, we have to run on battery power, and I have to pop out a battery on the bottom just like this, and then get a new battery and put it back. Occasionally I'll get caught and I'll just run out of energy.
Eric's arm, although not perfect, has changed his life. So will this technology one day be able to improve our brains as well as our bodies? This stroke victim can't move or speak. But an electronic brain implant gives him the ability to operate a computer by the power of thought alone. His thoughts generate electrical activity in the implant, which is picked up by an aerial link to the computer. The signals are then translated into action, and the cursor moves on the screen.
The brain is able to communicate with electronic devices really because they speak the same language, which is electricity.
A two-way signaling system is being developed so that implants can also receive information from other parts of the body.
We want to bring touch into the brain directly using stimulation through arrays of electrodes in the brain. And we think that it will be possible someday for people who are quadriplegic to be able to feel their body again.
External brain stimulation is already being put to the test. This is the world's first radio-controlled rat.
I didn't set out to make Jihad Ninja rats. What we wanted to do was an experiment that gave us a sense about how well animals understand signals that come directly into their brain.
Rats have poor eyesight. They use their whiskers to find their way around in the dark. 3 electrical probes, each the thickness of a single hair, were implanted in the part of the rat's brain that picks up signals from its whiskers. The operator can direct the rat by typing commands into the computer.
In one way, you could compare the system to a child's remote-controlled car. An operator stands with a laptop and sends out key signals.
When the signals are turned off, the rat becomes confused until the next signal is given. Dr. Talwar believes his remote-controlled rats could be very useful.
At the time we were doing the experiment, 9/11 happened in New York, and we were looking at these images on television, and it occurred to us that what we have in front of us could be a very cool technology to solve many of the search and rescue problems.
Rats could be invaluable for search and rescue amongst wreckage, or for sniffing out hidden landmines. Unlike clunky machines, rats are familiar with rough terrain and small spaces. The concept has not been well received by animal rights groups. Such experiments will be regulated and may be limited if they're shown to cause unnecessary harm or stress to the rats and mice. But one day, humans might choose to have brain implants themselves.
As the baby boomers of the world get older and older and more scared of falling apart, I think you'll see lots and lots more medical pressure to augment our bodies and improve them through putting direct silicon digital connections inside our bodies. We've seen time and again that what starts out as a technology for helping people who are ill or sick or injured then becomes optional. And the great example of that is cosmetic surgery. It started out for helping people with burns, but now cosmetic surgery has a whole life of its own for improving people's looks and well-being.
If this is what we're prepared to do to make ourselves more beautiful, what would we do to be brighter, more talented, more athletic?
We could give people supranormal senses. We can give them the ability to have ultrasound. If you have ultrasound, then you can detect the presence of objects near you without seeing them. You might be able to use infrared, which would allow you to see in the dark. You might have supranormal reflexes. You'd be able to hit a baseball coming at you much faster than you can now.
Once you have that, it's not very far to getting a wireless internet connection inside our head. So I fully expect 20 to 25 years from now, a lot of us, our grandchildren especially, will be walking around with wireless internet connections.
And there will be robotic devices throughout our environment. Millions of chips will be embedded in our furniture, utensils and clothing.
Like in a Disney movie, we'll talk to tea kettles and teacups, and we'll talk to our furniture. And instead of having a robot doctor, our robot doctor could very well be our clothing, for example, with chips in it. Our clothing will monitor our health, our heartbeat, monitor our bodily fluids, and in case of an accident, our clothing will alert the authorities and download our entire medical history before the ambulance arrives.
The rise of machines could be just around the corner. And this may be a source of hope, not fear, because the robots running our lives are unlikely to be the metal and silicon creations of science fiction. They'll be part of us.
The future of robots is us, and us will be the robots. The combination of person and robotic technology is going to be far better than any pure robot that we can build.
Our new robo-beings. A collaboration of man and machine, flesh and technology. Not Homo sapiens, but Robo sapiens. United in structure, brain, heart, and soul.
Next tonight, there's a terrifying game of cat and mouse off the coast of Bermuda when American and Soviet subs collided. Nuclear sharks after the break.
The battlefields of the future will be more dangerous than ever. In the 21st century, there will be threats to our freedom and security like never before. But will we be ready? Battles will be fought on land and sea, but they will not be won without supremacy in the air. Enter the incredible world of 21st century combat.
Air power is the dominant strategic force. It's air power that lets you influence events and respond to events quickly. It's air power that lets you fight a war without putting hundreds of thousands of people on the ground.
To date, Air Force F-15s have won more than 150 dogfights against enemy fighters without a single loss. And the Navy F-18 Hornet is widely recognized as the world's best carrier-based fighter-bomber. But in the future, neither the F-15 nor the F-18 will be able to survive against deadly enemy anti-aircraft missiles.
Surface-to-air missiles, or SAMs, are going to represent the biggest threat. Those very formidable systems developed in Russia or China will have to be taken out of action very quickly in any future conflict.
The fighter of the future will need to be stealthy to slip past enemy radar. It must be able to take out anti-aircraft installations. And it must out-dogfight any enemy fighters that get in the way. That future fighter is already here. The F-22 Raptor, the air dominance fighter of the 21st century. Developed by Lockheed Martin, this advanced tactical fighter has been designed to be the first plane to cross enemy lines, clearing the way for all other forces.
The F-22 is both an air-to-air fighter and an air-to-surface fighter, so it can drop precision weapons.
That means it'll be able to go in early in a conflict, knock out all the air defenses that an enemy has, and also take out certain ground targets. And open the door for all the U.S. forces, whether they're ground vehicles or other aircraft, to come in and continue the fight.
The development of the F-22 Raptor first began in 1985, when the Air Force requested proposals for an advanced tactical fighter jet to replace the F-15 air superiority fighter. Military planners feared that the F-15 would not be able to counter new air and ground threats on the horizon. The result was the creation of the F-22.
The capability of the aircraft is a quantum leap above what exists right now, and it's going to take air power and revolutionize it into a whole new world.
In the battles of the future, stealth will be critical for all new fighters to avoid being seen by enemy radar.
Non-stealthy aircraft just will not survive in the air battles of tomorrow.
Stealth technology was created to counter advances in radar. Radar works by sending out radio waves and measuring the amount reflected back to determine the distance, speed, and course of an object. But stealth aircraft are designed with surfaces that deflect radio waves away, making them nearly invisible to radar. The world's first stealth production aircraft was the F-117 Nighthawk.
The reason that airplane is faceted is a limitation of the computer technology at the time. It's easier to model a finite number of flat surfaces than it is a bunch of curved surfaces.
And while the aircraft was a breakthrough at the time, the facets limited the plane aerodynamically. But now, thanks to more powerful computers, engineers can design aircraft that do not have to sacrifice aerodynamics for stealth.
The F/A-22's aerodynamic slickness allows it to have the lowest drag of almost any aircraft ever produced.
The F-22's aerodynamic superiority, combined with its stealth and firepower, make it a far better adversary than any aircraft before it. The F-15, which the F-22 will replace, has been a very successful fighter, but it is not stealthy. The F-117, while stealthy, carries no air-to-air weapons and is not designed for air combat. It relies on stealth and mission planning to protect itself. But the F-22, on the other hand, is not only stealthy, but comes with a full complement of air-to-air and air-to-ground weapons.
The primary armament is in weapons bays underneath the airplane, where we carry 6 medium-range radar-guided missiles.
By carrying the weapons internally, it preserves the stealthy shape of the plane. For closer infighting, the F-22 has short-range missiles and guns.
Behind these two doors right here is the side weapons bay. This is where we carry a heat-seeking missile. For close-in armament, the Raptor is equipped with the M61A2 cannon. The muzzle is hidden right behind this door right here. It's hidden because of the stealth characteristics of the airplane. Cannon carries 480 rounds and is capable of shooting 100 rounds a second.
The F-22's advanced weapons systems will make it a formidable interceptor, as will its unique ability to find enemy aircraft without revealing its own position. When other planes use their radar, they become visible to every other radar system in the area. But that's not the case with the F-22.
Perhaps the highest tech part of the airplane is the radome itself. Not only does the radome have to be stealthy, but it has to be able to transmit and receive its own radar signals.
How the F-22 radar achieves that remarkable feat is classified. But what is known is that the F-22 can see enemy aircraft at a distance while remaining invisible to them.
The first time that the bad guys will really know there's an F-22 in the area is when one of them blows up.
Along with its advanced radar system, the F-22 is the first fighter to have supercruise, the ability to travel faster than the speed of sound without using its afterburners. A jet's afterburners boost speed by pouring fuel directly into the hot blast of the engines, adding fiery extra thrust. But afterburners are also wasteful, consuming enormous amounts of fuel, dramatically affecting the range and duration of a plane's mission. But the F-22 doesn't have that problem. Without using afterburners, it can supercruise at an incredible 1.5 times the speed of sound, over 1,000 miles per hour.
This is all about our pilots being able to go fast, minimize the amount of time they are exposed to any threat, do the mission that we've sent them to do, turn around and come home safely.
The F-22 is presently the only fighter in the world with supercruise, but it wouldn't be possible without a very unique set of engines.
The goals for Pratt & Whitney were to provide a transformational engine that the Air Force needed, one that was stealthy, maintainable, and fast.
The F-119 PW100 was developed by Pratt & Whitney after years of research. It sets the new standard for jet engines. Along with its incredible supersonic ability, the F-119 incorporates thrust vectoring.
Here we are at the rear end of an F/A-22 Raptor. First thing you'll notice are the nozzles for the F-119 engines. In flight, during a maneuvering dogfight, they actually move up and down and vector the thrust of the engine to provide maneuverability.
It helps us turn inside any foe, maneuver at low or high speeds to outmaneuver another airplane, or potentially an enemy weapon that's headed towards us.
The F-22's stealth, supercruise, and vector thrusting are impressive breakthroughs, but its most outstanding feature may be its ability to nearly fly itself through advanced computerized controls.
It relieves the pilot of all the duties, gives the pilot total freedom to just look out engaged in a combat scenario.
In addition to monitoring its own performance, the F-22 constantly gathers data on other aircraft in the combat area and presents the most important information to the pilot.
We're going to have information passed to us from either unmanned vehicles or from off-board sensors so that we can integrate data and use that information for targeting. And it's the way that we are driving our forces in warfare. We are much more integrated with both other services and with other platforms, and the F-22 fits right into that concept.
The F-22 Raptor's total package of avionics, stealth, supercruise, and thrust vectoring make it the most technologically advanced fighter today.
I've never been in an airplane that accelerates as fast, that's as agile, the ability to turn very sharply, and it just brings a great combination of the speed, the stealth, and the avionics to the fight that nobody else is going to be able to touch.
But there will be future competitors, like the Russian Sukhoi 37, which features thrust vectoring and a radical forward swept-wing design. And the fifth-generation MiG, the 1.22, which some have nicknamed the F-22ski.
The Russians are still very active aircraft developers. They've got a variety of technologies that they're continuing to improve upon and that can be made available to our future enemies. And so that's why we have to stay on top of the technology that we are developing and make sure that it is able to take out anything that other countries develop.
When you look at the adoption by China of the Su-27 and the fact that it'll probably be modernized and improved, that brings up the need for more advanced fighter aircraft in the US. And that's one of the main reasons, I think, why the Air Force is so insistent on the need to have the F-22.
In addition to Russia, other U.S. allies are producing advanced interceptors for export that are superior to the F-15, such as Sweden's JAS-39 Gripen and France's new Rafale. Germany, Italy, and the UK have joined forces to create a Eurofighter, the Typhoon. If these planes fall into unfriendly hands, the U.S. Air Force will need the F-22 to maintain their advantage.
We're always going to go into war wanting to have that air dominance, and the F-22 is going to be the big boy on the block that can help us to do that.
In future combat, the F-22 is to be joined by another stealthy aircraft, the F-35 Joint Strike Fighter, the ground attack bomber of the future. Designed for the U.S. Air Force, Navy, Marines, and Britain's Royal Navy, the question is, will it work for every user? The rules of war have changed. Brute force has given way to high tech, and conventional weapons of the past will no longer be effective. In future battles, the F-22 will be the first fighter to cross enemy lines, surgically removing air and ground targets. Next in the F-35 Joint Strike Fighter, the attack bomber of the future. It will assume the air-to-ground attack role for the U.S. military. The F-35 can carry heavy weapons externally for maximum effect. But when a smaller payload is carried internally, it is nearly as stealthy as the vaunted F-117 Nighthawk.
It has a significant amount of stealth capability to allow it to be used early on in a campaign, and it has a significant amount of weapons carrying and payload capability to be used at the later stages of campaign. The threat to the airplanes may not be as significant and require less stealth.
The development of the F-35 was driven by the Armed Forces' desire to save costs by creating a ground attack bomber that would meet the needs of the Air Force, Navy, Marines, and Britain's Royal Navy.
Airplanes are becoming very expensive these days, and We had to do something to get the cost of these airplanes back down to a reasonable level.
The F-35 is expected to cost about $40 million, 1/3 the cost of an F-22 Raptor. But could one basic airframe be designed to satisfy so many different military demands? Each armed service wanted a stealthy ground attack bomber, but the Marines also needed a plane with short takeoff and vertical landing capability. The U.S. Navy required a craft with larger wings, heavy-duty landing gear, and an arresting hook for carrier landings. And the wings would have to fold up to save deck space.
The size and scope of the JSF program is pretty significant. The airplane is being designed to replace the F-16 and the A-10 for the Air Force, the AV-8B for the Marine Corps, and the FA-18 for the Navy.
Unlike the twin-engine F-22 Raptor, the F-35 Joint Strike Fighter was designed around a single engine to keep down not only costs, but weight. A lighter plane can carry more weapons.
For the Joint Strike Fighter, one of the keys of its mission is the ability to handle a large amount of ordnance and bring it to an enemy site. That all works better with a single engine.
The Air Force version of the Joint Strike Fighter, the F-35A, made its first flight attempt on October 24, 2000. Tom Morgenfeld, who had been a test pilot for the F-22 Raptor, was at the controls.
Well, a million things are going through your mind. Your eyes are everywhere, you're listening, you're watching. Your senses are tuned to an incredible level because you're sensing and feeling the airplane for the very first time. It flies wonderfully. It's definitely a pilot's airplane.
The Air Force testing went smoothly. Next, a Navy version was built with heavy-duty landing gear and wider wings for the slow speeds needed to land on carriers. Navy test pilots flew touch and goes, demonstrating the F-35's ability to land within the space of a carrier's flight deck. But the most difficult challenge still lay ahead for the F-35 program. The Marine Corps needed a version that could perform short takeoffs and vertical landings, STOVL for short.
The STOVL capability is extremely important to the Marine Corps because the airplane can go just about anywhere that the rest of the forces can go. It's not limited to needing a large runway. It doesn't need a really big ship to operate off of.
Engineers at Lockheed Martin, the designers of the F-35 Joint Strike Fighter, took a hard look at the AV-8B Harrier, the STOVL fighter that the new aircraft would have to improve upon.
The Harrier is a great airplane if you look at the fact that it's basically 1960s technology. It's achieving all those wondrous STOVL flight sort of maneuvers without the aid of a lot of computers.
The Harrier's ability to take off, hover, and land vertically is achieved by vectored thrust. The powerful force of its jet engine is directed downwards through 4 nozzles that can pivot 90 degrees.
I was brought in because I am a Harrier pilot with almost 1,600 hours in that airplane. So all of the lessons learned I have from the Harrier airframe and operational experience I have, I was able to bring to the program and use those to help evaluate the X-35 STOVL version.
For hovering, engineers gambled on a radical new system. They planned to supplement the vectored thrust method by harnessing the jet engine to a drive shaft that would power a fan to blast air downward.
In 1991, we unveiled this shaft-driven lift fan system to the technical world. Some actually said, "You gotta be kidding me. Are you guys serious?"
The lift fan required doors to open behind the pilot on the top and bottom of the plane to draw in more air. The fan would blast air down mid-ship, while the jet nozzle in back swiveled, blowing its powerful exhaust down to create a balanced lift force.
The shaft-driven lift fan system allows you to harness a lot more energy out of what the engine is producing.
But harnessing a jet engine to a drive shaft proved to be extremely difficult.
The mechanical energy we were dealing with in the shaft-driven lift fan system was very large. We had 28,000 horsepower being transmitted from the drive shaft from the main engine to the lift fan. And that's similar to the power going through a U.S. naval destroyer.
The lift fan's ability to blend large amounts of cool air with the hot jet exhaust provided another important benefit.
One of the things we learned in JSF was to combine the jet exhaust to get a lower combined temperature than the Harrier. This allowed us to avoid some of the problems with concrete, where the concrete would actually burst and explode under the high temperature and high jet exhaust from the Harrier.
At the Lockheed Martin test facility in Palmdale, California, the revolutionary lift fan system was put to the ultimate test, in the air. If the lift fan failed during hover, the plane would crash.
It made its first flight in 2001, and it was a complete success. And at that time, I didn't hear any more from the people who had been saying for years, this thing will never work. It worked.
Now, all three versions of the F-35 for the Air Force, Navy, and Marines are being developed and further tested for mass production. The United States, Britain, and their allies are expected to order more than 4,000 Joint Strike Fighters, which will replace most American-built fighter bombers in use today.
The handling qualities and performance are stunning. It really is a pilot's airplane. It sort of makes you feel like a little boy. You want to take it home and tuck it under the pillow with you at night. It's just a pilot's airplane.
In future air conflicts, the F-22s will be used to establish air dominance. Then waves of stealthy F-35 Joint Strike Fighters will use their superior weapons-carrying abilities to attack other major ground targets.
The Joint Strike Fighter is going to be the backbone airplane for hauling freight. It is going to be the muscle part of sustained forces.
Commanders can also alter an F-35's mission in the air as situations change during the battle.
There are a variety of ways for the F-35 to bring in information from external platforms, other airplanes flying around the battlefield, satellite-based assets, ground-based assets. All that information can be presented to the pilot in the cockpit and allow him to be more of a tactician and manage the tactics of the game that day instead of worrying about the nuances of flying the airplane.
The pilot's job will be to supervise the process of identifying the target and then to give consent for weapons release.
The Joint Strike Fighter will be able to carry a wide range of weapons, to include the heavier weapons such as the 2,000-pound bunker busters and 2,000-pound blast weapons.
The Joint Strike Fighter's 1-ton bunker busters and blast bombs will be guided to their targets with pinpoint precision by JDAM tail kits. The Joint Direct Attack Munition, or JDAM, is a kit that can be put on any bomb to give it the brains to know where to go, and the movable tail fins to guide it there.
JDAM is a guidance kit that came after Desert Storm. This little round piece on the side there is an inertial navigation clock. Now this clock, instead of measuring seconds, measures feet. If you take the unit and you tell it where it is right now electronically, and then you move it back a foot, or you move it up a foot, it measures every centimeter and every distance.
The bomb knows the coordinates of where the airplane is, and it also knows the coordinates of where the target is. And when the weapon is released from the airplane, it simply flies from one set of coordinates to the other and does its thing when it gets there.
Because a JDAM is directed by GPS, or global positioning satellites, it can hit targets regardless of visibility.
The way we use it is by employing it against targets that we cannot normally see visually, whether it is due to weather, smoke, haze, or just some sort of other thing that's obscuring the target.
As a JDAM falls, its inertial clock keeps track of its position and signals the tail to make course corrections, directing it to the target. The accuracy of new weapons like JDAMs will reduce collateral damage. It also makes the F-35 an even more formidable weapon system.
The new weapons, such as JDAM, really reduce the need for the number of sorties, and that reduces our risk because we're not exposed to enemy threats as often.
The F-35's combination of advanced weapons, avionics, and stealth will help it ensure its success over the battlefields of the future. U.S. military planners wondered if these same features could be utilized in a helicopter. They wanted a stealth helicopter. But could it be done? Over the last 50 years, helicopters have evolved from slow-moving multi-purpose support vehicles to fast-moving frontline attack ships. But in the high-tech wars of the future, speed alone is not enough. Information is the key.
There's three elements that are critical to warfare. The ability for you to know more than the enemy, the ability to maneuver quickly around an enemy and gather more information about them, and the ability to provide precision firepower at the enemy.
In future conflicts, after the F-22 Raptors and the F-35 Joint Strike Fighters have cleared the way, surveillance and attack helicopters will support ground troops as they move in to secure the area.
We like to be down low where the action is, and we like to be down low where the threat can't see us.
But at such low altitudes, helicopters are vulnerable to a wide assortment of ground-to-air weapons.
All the simple systems, the guns, unguided rockets, the surface-to-air missiles, it's got to deal with all of that, and it's got to deal all of it effectively.
The Pentagon has responded with a two-pronged strategy to counter this threat: inexpensive, expendable unmanned helicopters and stealthy manned helicopters. Unmanned helicopters will be primarily used for surveillance and for gathering targeting information. Fire Scout, designed by Northrop Grumman, was specifically developed to take off and land on Navy ships. However, the key to creating a successful manned helicopter for future combat is to make it stealthy like the F-22. But the question is, can it be done?
Achieving stealth in a helicopter is different from stealth in a fixed-wing aircraft. You're concerned about different signatures: radar reflectivity, infrared, noise, all things that will give away an aircraft's position.
Those signatures, like heat, smoke, and sound, put helicopters and their pilots at serious risk over the battlefield.
All the small shoulder-fired missiles, which are very effective against helicopters, are heat-seeking infrared systems.
The challenge for engineers was to create a quiet helicopter with very few signatures and a small radar cross-section. And that's exactly what Sikorsky has done with the new RAH-66 Comanche.
In the Comanche, with all the stealth capabilities, we can defeat the radar threat. We can defeat the guy with the shoulder-launched heat-seeking missile. And from the guy popping up in the tree, our agility defeats him. Our small size, our quiet acoustic signature defeats him.
Often the first thing you hear from a helicopter is the sound of the wake from the main rotor hitting the wake from the tail rotor.
In the Comanche, the fan tail is shrouded, so there is no interaction between the fan blade tips and the main rotor tips, and it's also canted slightly. And those all contribute to reducing the acoustic signature.
Engineers also experimented with the main rotor to find a quieter design.
If you look at a Comanche, it's got a 5-blade rotor, and what that does is it cuts down the normal chop, chop, chop sound from a helicopter into a more discreet whir that kind of blends into the background.
Reducing the heat signature of a helicopter is also essential to making it more survivable.
When you look at a Comanche, the first thing you ask yourself is, where's the exhaust? Where does all this hot air get out of the engine?
The Comanche's exhaust actually escapes through the tail boom, where it is instantly dispersed by cool air from the rotor.
That missile has to have something to home in on, and that's a heat signature. Comanche defeats that by the engine exhaust being mixed with ambient air and cooling it so that there's no longer a heat plume for that missile to home in on.
To defeat radar, the Comanche utilized the stealth secrets first developed for the F-117 Nighthawk. There are no radar-reflecting right angles on its outer fuselage, and all weapons are carried internally to help keep its stealthy shape.
What's interesting about the helicopter is some of the things that achieve stealth actually make the helicopter better. Things like the retractable landing gear and the retractable weapons bays. That also makes it sleeker and faster. So once you've bought into the stealth part of it, you get other superior attributes.
The main role of the Comanche is to give commanders an overview of the battlefield by providing up-to-the-minute information.
Comanche is going to be basically their flying cavalryman. It's going to dart in and out, slash and cut, be a reconnaissance vehicle.
As Comanche's two pilots gather data, their computer shares that data with other Allied forces.
When the Comanche finds the enemy, he's going to kind of direct like a quarterback to apply the firepower to defeat that enemy.
Engineering advances have also made the Comanche one of the easiest and most forgiving helicopters to fly.
One thing that Comanche brings that other previous generation helicopters can't bring to the table is the pilot can maneuver the Comanche in virtually any axis without fear of exceeding any limits.
Although it will be used primarily for reconnaissance, the Comanche will also be armed for self-defense.
The Comanche is capable of carrying a wide array of weapons, all the way from guided missiles using a laser guidance system, heat-seeking missiles, which would be more of an air-to-air weapon, or unguided rockets, and also the latest Hellfire is pretty much a fire and forget.
In addition, Comanche's pilots can ask Allied aircraft to fire missiles their way, and can then take over and guide those missiles to their targets. If the Comanche is hit, its computer system can often fix itself by reassigning vital functions to undamaged computer cards.
This is where the computer brain of the Comanche is.
In support of its reconnaissance mission, Comanche can control as many as 5 unmanned aircraft.
When the Comanche may be employed, it may have little vehicles that it launches out, so it has its own little eyes over the hill so it can see what's going on without putting itself at risk.
In addition to launching its own unmanned air vehicles, Comanches may be aided on the battlefield by swarms of LOCAS, small intelligent missiles with their own computer brains.
It's about 31 inches long, weighs a little over 100 pounds, carries a single warhead, has a laser radar. In other words, it has a scanning laser beam that generates pictures.
The LOCAS also communicate with each other and cooperate in searches and attacks.
You could have a swarm of LOCASes, each of which has its own eyes, each of which is thinking, but each of which is communicating with each other. Send that imagery back to the operators who could either use these as surveillance probes or, in fact, as weapons themselves.
Weapons like LOCAS reflect the trend toward electronically linking all Allied forces and weapons so that information can be shared and used by all. By networking aircraft over the battlefield, with surveillance platforms and other weapons systems, commanders can quickly change missions to take advantage of up-to-the-minute information.
The key to the air battle of the future is not necessarily stealth, speed, or firepower. It's going to be information.
Unmanned air vehicles, or UAVs, will provide a large part of that information while flying long-duration surveillance missions. So, will the Air Force of the future have no pilots? Since the very first use of airplanes in war, military planners have looked for ways to make aircraft more effective and more lethal. Once so secret their very existence was denied by the government, unmanned air combat vehicles, or UCAVs, are now poised to take the preeminent role in 21st century air combat.
UAVs are certainly going to change air power in the 21st century. You can see it starting to happen today, but what we're looking at now is just the beginning, because there's going to be more of them, and they're going to be better.
Unmanned aerial vehicles allow the military to do more with less, to put more aircraft into the air than you otherwise would be able to because of the limited number of pilots that you might have, or where it might be too risky.
In the future, aircraft that have no pilots on board will carry out the most dangerous combat missions. Today, unmanned air vehicles, or UAVs, are already taking over the role of long-duration surveillance.
UAVs don't have mothers. You lose a UAV in combat and nobody bats an eyelid.
One of the earliest surveillance UAVs was the Predator. It was developed in the early 1990s.
When you look at Predator, basically they start off as being long-endurance systems that can really persist over the battlefield.
In Afghanistan, Predators provided critical real-time intelligence. And it was there that a Predator made an amazing transformation from surveillance to armed aerial attack.
Fired a Hellfire missile, an Al-Qaeda convoy, and destroyed one of the vehicles in there. And at that point, it crossed the line from an unmanned aerial vehicle into an unmanned combat aerial vehicle.
Today, the new Predator B can carry up to 10 Hellfire missiles. Of course, its primary mission is still what the military refers to as ISR, or Information, Surveillance, and Reconnaissance.
It's basically a poor man's satellite. I mean, you can bring it in and let it dwell in an area.
UAVs transmit important visual information to battlefield commanders via satellite or other data links.
Once targets had been located, identified, and cataloged, these could be disseminated to other weapons or weapon systems.
Reconnaissance UAVs have multiple ways of conducting surveillance. On clear days, they use specially stabilized optical lenses that can zoom to high magnification. At night, they use infrared, and under adverse conditions, they use synthetic aperture radar to pierce the thickest clouds, sandstorms, or oil field smoke. When the radar is reflected back, it can also be used to create a 3D image of objects.
If the enemy chooses to use countermeasures or decoys or deception techniques, having to beat 3 systems is a lot harder than 1.
The success of the Predator paved the way for the development of an even more advanced high-altitude jet-powered UAV by Northrop Grumman. It's called the Global Hawk, but unlike the Predator, it was designed to take off, fly its pre-programmed mission, and land all on its own, thanks to the GPS, or Global Positioning Satellite System.
The Global Hawk is basically a much larger version of the Predator. It has higher altitude capabilities, increased payload. It can carry a lot more sensors, a lot more communication devices, and it can loiter over a battlefield for up to 35 hours.
The Global Hawk can stay aloft for a day or more, providing constant near real-time video surveillance over an area the size of Illinois.
Predator and Global Hawk give us an up-close view, which is something you can't get from a national asset, which would be a satellite type of thing.
Though still in development, the Global Hawk had a dramatic impact during Operation Iraqi Freedom. A single prototype provided information to Allied forces on 55% of all time-sensitive targets, including mobile Scud missile launchers. Like the Air Force, the Navy wanted its own autonomous UAVs. However, designing one to take off and land on an aircraft carrier was a tremendous challenge. But the engineers at Northrop Grumman were up for it. In the summer of 2000, they began working on the X-47 Pegasus.
The hardest part of the Pegasus program was definitely the flight controls. Getting on and off an aircraft carrier, of course, is one of the toughest design problems for an aircraft. And doing this with a tailless vehicle like Pegasus certainly was the toughest problem we had.
That problem was solved by using 6 innovative surfaces to make the plane climb, descend, and turn.
This surface just rotates up. The elevon, of course, both up and down, and then there's another inlay on the lower surface as well.
The first flight of Pegasus, the demonstration was very, very successful. It lasted approximately 12 minutes. There was no human in the loop.
But could Pegasus, without any human assistance, land within the tiny space between the arresting cables of an aircraft carrier? The engineers came up with an ingenious way to find out.
And we actually glued a small paintball down onto the bottom of the hook so we could get a clear touchdown point. That was quite an achievement that we're very proud of.
The Navy will use its stealthy UAVs to get targeting information for its guns, missiles, and fighter aircraft.
The initial focus has been on information, surveillance, and reconnaissance to provide targeting information to the Navy's strike packages.
But many future UAVs, such as Boeing's X-45 unmanned bomber, will be heavily armed. Although flying pre-programmed missions, armed UAVs will still need human permission to fire.
It has to know where friendly forces are on the ground, where civilians might be, where collateral damage, i.e. hitting a church or a mosque, might be an issue. So there is an element that we always retain where a human in the loop is important.
You can have a weapon that's doing its own surveillance and has its own ability to engage a target. And that gives you a level of dominance that we're just emerging on right now.
In the not-so-distant future, there will be even more radical aircraft and airborne weapons systems. Everything from electromagnetic pulse weapons to powerful airborne lasers to hypersonic aircraft that can fly to anywhere in the world in 2 hours or less. But how soon will these high-tech secrets become a reality? The enigmatic F-117 stealth jet flew in secret for 10 years before its existence was revealed to the public. Some of the unclassified projects that are acknowledged by the Pentagon seem more like science fiction than reality. The military is designing a weapon system designed to neutralize an enemy encampment or factory without destroying it and scattering nuclear, biological, or chemical materials. Electromagnetic pulse, or EMP weapons, will blast a highly concentrated magnetic field towards its target, overloading and destroying any electrical components.
The small electromagnetic pulse weapons offer some pretty startling capabilities. You can essentially completely destroy an enemy's electronic infrastructure in a very precise way. You can fly over a small facility, only a couple of acres, fire it, and suddenly none of their computers work, none of their weapons work, none of their electronics at all will work.
Researchers are also experimenting with an airborne chemical laser.
An entire aircraft has been turned into a chemical energy plant that points that laser at a target and burns through missiles.
This aircraft will fly at higher altitudes and will primarily be used for Scuds or for ballistic targets that would be fired from one country to another.
American generals don't want a fair fight. They want their equipment to be the absolute best in the world so that whatever they come up against, they can defeat it quickly and efficiently.
The battlefield of the future will continue to be a dangerous place. But military planners believe that the key to maintaining the security of the United States is to develop the weapon systems of tomorrow, today.